the notes for AP Calculus on the topic of the first fundamental theorem of calculus. So the first fundamental theorem of calculus, remember, is when you have definite integral from a to b of some function, in this case it's labeled f prime of x, then you evaluate that by first integrating. When you integrate f prime of x, that gives you back the antiderivative, which is the original function, f of x, and then you substitute it in the upper limit first, so that's f of b, and then subtract what you get when you substitute in the lower limit, which is a. But we're going to look at this in a slightly different way to see how that can help us solve some different types of problems. So let's see what would happen if we added f of a to both sides of the equation. Well, that would give us the f of b by itself. And let's just switch the sides of the equation here. So we'd have f of b isolated on one side of the equation equals, on the other side, we'd have f of a plus the integral from a to b of f prime of x. And this is the form we're going to use the first fundamental theorem of calculus in today's lesson. So, one way of thinking about this, so I've got one graph here we'll use in just a little bit. So let's just draw a little graph right here, the x and y axis. And let's just look at some interval from a to b. Let's say here's a and here's b. And f of a and f of b just represent the y value. So let's say f of a is right here. And let's say f of b is right here. In other words, the function has a point right here at a f of a and then another point here at b f of a. This is on the original function. So this tells you on this interval, this f of a, this is kind of like the initial y value, right? On this interval, this is the y value it starts at, so we're going to refer to this value as the initial value we know. Plus, well, when we add this definite integral, we end up getting the final value of this interval, f of b. Well, if that's the case, then since we're adding this, this must be how much the function changes, starting from f of a and ending up at f of b on the interval from a to b. So we're going to refer to this definite integral of the derivative as the change in the original function on the interval a to b, as it ends up right here. Or another way of thinking about that, if we had, let's say, this is the graph of the original function. Let's say the graph of our derivative looks like, say that, on the interval from a to b. Then, remember this definite integral, one of the meanings of it, it represented the area between the curve and the x-axis, and it still does, but we see that area has more meaning than just area. This area, or this definite integral, represents the change in the original function f of x on the interval from a to b. So it means more than just area. So I refer to these as initial plus change problems. And the way you can recognize them is it's when you're looking for one point of the function, f of b, you have another point, which is your initial, f of a, and you have something about the derivative so that you can integrate from a to b to get what the change is. So let's look at an example here, where it's more of an abstract example first. Well, we're given the derivative, f prime of x, is 4x minus 3. We're also given one point on the function, f of 2 is 7, and we're looking for another point on the function, f of 5. So in this case, the 5 is like our b here, and the 2 is like our a. So this is an initial plus change problem, so we're trying to find f of 5. And that would equal the initial value, f of 2. And I know that we know that's equal to 7, but easier to set up if you put the 7 in as your next step. And then plus the change, so this is our initial here, the change comes from the definite integral from a to b. In this case, you can see right here, it's from 2 to 5. How much does the function change on that interval? And then what has to go here is the derivative of this function, f prime of x, which we have right here, is 4x cubed minus 3. So now we know f of 2, well, that initial value we know is 7, initial y value. And then plus, then we just have to integrate this and take a look and see if we can just integrate it like this or if it would require u substitution. Well, you can see there's not really a function inside, and these are just subtracted. So we can just integrate each one separately. So this one would not require u substitution. You'll see on today's notes, some of these will require u substitution and some will not. So we get the 4. Constant stays out front. When you integrate x cubed, you get x to the 4th over 4. Minus, when you integrate a constant, 3, you just get 3 times the variable, which is x, 3x. And then that's evaluated from 2 to 5. And then you can see we can simplify that a little bit. The 4's reduce out, so it's just x to the 4th. So you've got 7 plus, that's our initial. And then let's go ahead and substitute in the upper limit first. So that'll be 5 to the 4th. Minus 3 times 5, and then minus, in parentheses, I'm not correcting the whole thing, this is more than one term here, so that'd be 2 to the 4th minus 3 times 2. And let's just simplify this now. So I've got 7 plus, well, 5 to the 4th, 5 to the 3rd is 125. Times 1 more 5 is 625. And then 3 times 5 is 15. And then minus. We've got 2 to the 4th, which is 16. Minus 3 times 2 is 6. We've got 7 plus 625 minus 15 gives you 610 minus 16 minus 6 is 10. 610 minus 10 is 600. Now I could have added the 7 in earlier, but I kept it separate so you can see the two parts of what we found here. The 7 here represents the initial y value, and we just figured out by taking the definite integral from 2 to 5 of the derivative, 600 is how much the original function changes by on that interval from 2 to 5. It increases by 600 if we got a positive 600. If we had got a negative number, that would indicate how much it decreases by. So our y value, f of 5, is equal to 607. Okay, now let's take a look at one where we have the graph rather than the equation of the derivative. So this one says we have the graph of f prime of x. The derivative f is shown in the figure above. And we're given f of 1 is equal to 5. Then find the following. First one it asks for is f of 5. So our initial, this is again initial plus change. Our initial one this time is f of 1. That's what we're given. Plus the change comes again from the definite integral. In this case, from a to b is from 1 to 5. Of the derivative of whatever this is, and the derivative of f is f prime of x. But f prime of x, that's what we have the graph of, right, instead of the equation. So this time you just have to remember what this represents graphically. And we know f of 1 is 5 plus, well, the definite integral graphically, remember, represents the area between the curve and the x-axis. In this case, from 1 to 5. So from right here at 1 to right here. Well, we want this area right in here. Now, this is made up of geometric shapes, but the way we can get this area in here is if we take the area of this rectangle here, and then subtract the area of the semicircle. Wouldn't that give us the area in between, which is what we're looking for? So basically we're taking the rectangle there minus the area of the semicircle. So the area of the rectangle, well, it's got a base from 5 to 1, that's a base of 4, times the height is 3, minus, for the area of a semicircle, it's just half of a circle, so instead of pi r squared, it would be 1/2 pi r squared. But we can tell the radius, r, if this was a whole circle, the center would be right here, so you can see the radius be 2 to this direction, 2 to this direction, 2 to this direction, so the radius is 2. And then if we simplify that, 12, we get 4 times 3 is 12, minus 4 squared, sorry, 2 squared is 4, times a half is 2, times the pi that's still there. So 12 minus 2 pi is the area between the curve and the x-axis from 1 to 5, and that's what this definition will represent. So we just figured out it's 12 minus 2 pi. Add that to initial, gives you 17 minus 2 pi. That's what f of 5 is. All right, let's take a look at another one. This one says f of 11. So for f of 11, the initial we can still use is f of 1. Plus, this time the change interval would be from 1 to 11 instead of from 1 to 5. And again, what needs to go here, if this represents a change, it has to be the derivative of whatever this function is. In this case, the derivative of f is f prime of x. So again, f of 1 is 5. 5 right there. Plus, now this definite interval from 1 to 11, again it represents the area from 1 all the way to 11. So now we have to go a little further on our graph. We already know what the area is from 1 to 5. But now, we have to go all the way to 11. So let's find the area of this triangle here first. So 1/2, the base you can see is 2. The height is 3. So that gives you 3. Okay. Then we can split this one into a triangle and a rectangle. The area of the triangle is 1/2. The base is 3. Times the height is 2. So the 2's reduce out, we get 3. But remember, any regions below the x-axis, the definite interval gives you a negative area. And we'll see why in a little bit, another reason why that is. And then we've got this rectangle here. It's just the base is 1. The height is 2. So it's 2. But again, it's below the x-axis, so negative 2. So if we put those all together, 5 plus 12 minus 2 pi, plus 3, minus 3, and minus 2. That gives us our final answer there. Well, if we combine all the constants, we'll see that's 17. The 3's reduce out, minus 2. So that's 15. And then we still have the negative 2 pi. All right, now let's take a look at f of 0. So f of 0, again, we can use the same initial, f of 1. Plus the change, this time would be integral from 1 to 0. Oops. Whatever your initial is has to be start as your lower limit, and then to 0 is what we're looking for, of the derivative f prime x. So f of 1, that's still 5. Plus, now the system's a little bit different because the 1 to 0 here, that's not the standard order that these definite intervals in. The lower number should usually be there. So remember, all you have to do to flip that, if you're in the wrong order, is just make it negative. So that's actually going to make it, instead of a plus there, that'll make it a minus, because we had to flip the lower and upper limit. But again, this still represents the area from 0 to 1. So that's this little triangle right here. You see the base is 1/2, the base is 1, the height is 3, so we get 3/2. So sometimes you can end up with fractions there. Do 5 minus 3 halves. Well, 5 is the same as 10 halves. Minus 3 halves gives you 7 halves. So that's what f of 0 is. Now let's take a look at f of negative 4. Well, we can still use the initial f of 1 plus the change, or do the integral from 1 to negative 4 of f prime of x. So f of 1 is 5. Again, though, notice these are in the wrong order, right? They're not in standard order. The negative 4 should be here, the 1 should be there, so you can just flip it. And again, that'll change that positive in between to be a negative. To be 5 minus. And then this represents the area under the curve between negative 4 and 1. Well, we already know what it is from 0 to 1. So from negative 4 to 1, we just have negative 4 to 0, we have to add the triangle right here. So that'd be 1 half. The base is 4. The height is 2. Which is reduced out, you get 4, but it's below the x-axis, so it's negative. So, it's negative 4 plus 3 halves in parentheses, just minus the whole thing. And then if we simplify that, we've got 5 minus, well, negative 4 is negative 8 halves, plus 3 halves gives you negative 5 halves. And then 5 is the same as 10 halves. And the negatives cancel out, plus 5 halves gives you 15 halves. Now, there's one more thing that's not on your problem set. However, I want to make a connection with something we did earlier this year. And that's, since we have the graph of the first derivative, let's see another way you can see why these represent the change here. So, remember when we have the graph of the first derivative and we want the number line for the first derivative? We'll just draw it right underneath here. And then label it f prime of x. And since this is already the graph of f prime, remember what you're going to look at is just the y values. So the y values you can see are negative here until 0, then they're positive all the way until 7, 0, and then negative the rest of it. And remember what this tells us about the original function f of x. When the first derivative is negative, when the slope is negative, we know the original function is decreasing. When the first derivative is positive, the slope is positive, so the original function is increasing. Then negative, back to decreasing. So, previously we just knew, okay, it's decreasing and increasing, decreasing. But because we have these areas here that represent the change in the original function, now we know exactly how much this function increases and decreases by. So we can see it decreases, and that's why this is negative, by exactly 4 on the interval from negative 4 to 0. Then from 0 to 1 it increases by exactly 3 halves. From 1 to 5 it increases by 12 minus 2 pi. From 5 to 7 it increases by exactly 3, the original function. But then from 7 to 10 you can see it decreases, and it decreases by exactly 3, which is why it's negative there. And then from 10 to 11 it keeps decreasing, it decreases by 2, the original function. So we have more information. We'll come back to this concept later on in this chapter. But that's another way to see that this is more than just area here. When it's the graph of the derivative, it represents the change in the original function, like we saw right here. Okay, let's take a look at some applied problems now. So this one says the particle moves along the y-axis with a velocity given by this function for time greater than or equal to 0. If the particle is at position y equals 5 at time 2, what's the position of the particle at time? Okay. So again, to recognize this as initial plus change, you can do that because we're looking for one point on the position function. We have one point on the position function, and we need its derivative. Well, remember the derivative position is velocity, and we have that as well. So this is an initial plus change. Now they don't tell you what to call the position function, but usually when a particle is moving on the y-axis, they'll call it y of t to remind you it's moving on the y-axis. So what we're looking for really is y of 4 would equal the initial. Well, initially we're given the position at time 2, so it'd be y of 2, plus the change, which comes an integral from 2 to 4, of the derivative of position, which is velocity, right here. So that'd be 3t squared plus 8. And now we know y of 2 is 5, so we can put in 5 right there. Plus, this one again, since they're just added and there's no function inside, we can integrate each one separately. No substitution required here. So when you integrate 3t squared, you get 3t cubed over 3. And then when you integrate 8t, 8 stays out in front, you get t squared over 2. Evaluated from 2 to 4. So initial again is 5. Plus, you can see that simplifies with 3's reduced out. And the 8, 2 goes into 8 4 times. So what we're left with here is 4 cubed plus 4 times 4 squared minus, put in 2, you get 2 cubed plus 4 times 2 squared. And we can just simplify this now. 4 cubed is 64. Plus up another 4 cubed is 16 times 1, another 64. Minus 2 cubed is 8. Plus 2 squared is 4 times 4 is 16. So you get 5 plus 64 plus 64 is 128. Minus 8 plus 16, 24. So our initial position was 5 plus 128 minus 24 is 104. That's how much the position function changed on the interval from 2 to 4, so we get new position at time 4 is 109 on the y-axis. In this case, it's position, so it's on the y-axis, you just say u. That's where it is on the y-axis. All right, let's take a look at the next one. This one, similar thing, except the particle is moving along the x-axis. And this time at time greater than 0, the acceleration is given by sine of pi t over 4. And we're told if the velocity of the particle is 6 at time 0, then what's the velocity of the particle at time 3? And again, the way you can recognize this is an initial plus change problem. We're looking for 1 point on the velocity function. We have 1 point on the velocity function. And we have the derivative of velocity, which is acceleration. So they all have those elements in common on these initial plus change problems. Okay, so we're trying to find the velocity at time 3. So v of 3 equals the initial one we're given is the velocity at time 0, so v of 0, plus the change would be the integral from 0 to 3 of, this has to again be the derivative of this function, and the derivative of velocity is acceleration. So sine pi t over 4. V of 0, we know the velocity is 6. Plus, this time notice we've got sine of pi t over 4, so there is a function inside. So this one will require u substitution. So off to the side here, you'd have to set u equal to the function inside. Now you could write it as pi t over 4, but then it's going to look like you have to use the quotient rule. But really this pi over 4 is just a constant you can pull out in front. So if you write it this way instead, that would be easier to tell that you actually don't need the quotient rule. Which makes it a derivative that one easier. However, remember on u substitution problems, if it's a definite interval, remember we have to convert the lower and upper limits. So if we substitute in 3 for t times pi over 4, well that's just going to make it 3 pi over 4. And when you substitute in 0 for t, well 0 times pi over 4 is still just 0. So we're going to say 0. And now we can rewrite this as the sine of u But remember, we need the whole integral in terms of u, so we need to replace this dt, and the way we do that is by taking the derivative of what we set u equal to. In this case, u dt, derivative of pi over 4t is just pi over 4. Just like the derivative of 5t would just be 5. Same rule for derivatives. The constant is on the front. Then, since we want to solve for dt and the derivative of u dt is a fraction, probably I think the simplest way to do that is to cross multiply. So we get pi dt equals 4 du. And then when you divide by pi, you end up with dt equals 4 du over pi. Now we can substitute that in for dt right there. So it's 6 plus, now we can pull out the constant of 4 over pi. And then what we have left is the integral from 0 to 3 pi over 4. And all that's left is a nice simple integral, just sine of u. But be careful, you can't add the 6 plus the 4 over pi right now. I'd be tempted to do that since they're right next to each other. But that would be violating the order of operations, remember, because you'd be adding before multiplication. So don't add that in until the end. And I keep writing it down here because a common thing to forget is the initial value. To evaluate the integral, just forget to add it. So if you keep writing it down, you're less likely to forget it. So we've got 4 over pi. And then when you integrate sine, you get negative cosine. But rather than putting the negative here, that's negative just a constant, it's probably easier if you pull it out in front and make that a negative 4 over pi. Then you don't have to deal with it when you're substituting in the lower and upper limit. So that way we can just have just cosine of u in there instead of negative cosine of u. And then we've got 0 to 3 pi over 4. So 6 minus 4 over pi. Then let's go ahead and substitute the upper limit first, so that'll be cosine of 3 pi over 4. And minus, substitute the lower limit 0, cosine of 0. So 6 minus 4 over pi times, well, cosine of 3 pi over 4. 3 pi over 4 is in the second quadrant here. This is pi, which is 4 pi over 4. So 3 pi over 4 is right here. You can see the angle there is pi over 4. So cosine would be adjacent over hypotenuse. Adjacent is negative 1 over hypotenuse is 2, radical 2. So that'll give you negative 1 over root 2, but that just simplifies to be negative root 2 over 2. Minus cosine of 0. 0 is right here under the circle. And so that's just 0.10. Cosine is the x-coordinate, which is 1. And you could leave it like that. But to make it a little simpler, you could distribute out that negative 4 over pi. So you get 6, and then the negatives cancel out here. So it's plus. And then the 2 also reduces into the 4 twice. So you get 2 root 2 over pi. And then negative 4 over pi times negative 1 would be a positive 4 over pi. And since these two have a common denominator, you might even combine those. You get 6 plus 2 root 2 plus 4 all over pi. But in this case, for velocity, it would be units per something. Seconds, minutes, hours, but we're not told the units per time in this problem, so we can't put the units down for what the answer is. All right, now let's take a little bit of a different problem here. It says capital G of x is an antiderivative for lowercase f of x. Remember, there's not a specific notation that represents the antiderivative. Unlike for the derivative, we have f prime, that's the derivative of f of x. So they're always going to define some function if you need some notation for an antiderivative in general. In this case, capital G of x. And oftentimes they will use a capital letter, but it doesn't automatically mean it unless they define it. Well, let's try to write that statement in reverse. Capital G of x is an antiderivative for f of x. Well, if you write it the other way around, starting with f of x, that means f of x is the derivative of capital G of x. And we'll see how that's helpful if we think about it that way. Notice just a slight difference in wording here. It says the derivative. Well, that's because there's just one derivative of a function. If you know the rules, power rule, chain rule, product rule, quotient rule, and the formulas for the trig functions and so on, then you know what the derivative is. There's just one answer. But notice that doesn't say the antiderivative, it says an antiderivative. Okay? And there's a reason for that. Because when you find an antiderivative, remember you have that unknown constant plus c, and that constant could be anything, so when you find the antiderivative, it's one of a possible set of possible answers, all with different constants. All right, so then it gives you g of 3 equals negative 5, and it says write but do not evaluate. That means you just have to set it up. An expression involving an integral, that gives you a little hint, that represents g of 7. That's what we're looking for. So this is, again, an initial plus change problem, but we just have to set it up, not work it out. G of 7 was what we're looking for, an expression for that. The initial we're given is g of 3 plus the change comes from the integral from 3 to 7. And then what goes in here has to be the derivative of g of x. So you could write it as capital G prime of x to start with. But then we know g of 3, so we got g of 7. We want an expression for g of 7, so g of 7 equals g of 3 we know is negative 5 plus, well, even though this is correct, chances are, since they defined capital G of x as an antiderivative for f, and we said f is the derivative of g of x, that means f is the same as g prime of x. So we could just write it as f of x. And so it says write but do not evaluate, an expression involving an integral that represents g of 7. And we just don't know. We don't have to work it out because we can't work it out really. We don't have the equation for f of x, and we don't have the graph of f of x either. All right, let's take a look at another applied one here. It says the rate of change. Remember, rate or rate of change is another word for the derivative. So the derivative of the altitude of a hot air balloon in meters per second, that's another clue at the derivative, whenever it's something per something, that's the derivative, for rate of change, is given by r of t equals t squared minus 4t plus 3. So even though they don't use the prime notation, this still does represent the derivative. Oftentimes they'll do that. They just call it r of t. I'm not using the prime notation. And it applies on the interval from 0 to 7. And then it says determine the change in altitude of the balloon during the time the altitude is decreasing. Okay. So this one's a little bit different than the other problems, because notice we don't have any points on the function, and we're not looking for any either. So this is like an initial plus change problem without the initial, but we're just looking for the change. So remember, the change comes from the integral from something to something of the derivative of, in this case, altitude, which they tell us the derivative of altitude is rt. So then this would have to be rt dt. So be careful. It's really tempting to say, oh, they give us an interval here. This must be from 0 to 7. But look at the wording of the question. It says determine the change in altitude of the balloon during the time the altitude is decreasing. And do we know for sure the altitude is decreasing between 0 and 7? No. It could be, but we don't know that. So no need to assume that it is. So it's like a two-part problem, essentially. That's the setup for the change. We're just trying to find the change, not the initial, just how much it changes on this interval during the time the altitude is decreasing. So we have to figure out the time the altitude is decreasing. Well, if you want to know when a function is increasing or decreasing, you have to use its derivative. Well, we already have the derivative of altitude right here. So the next thing you would do with that derivative is set it equal to 0. And then you can see this one factors into t minus 3 and t minus 1. and set those equal to 0 and factor form. Either t would equal 3 or t would equal 1. And look at our interval. Are those on are those relevant values on our interval, 0 to 7? Yeah, they're both in there. If they weren't in between 0 and 7, we'd cross them out. So then remember, you draw a number line. In this case, we're only looking between 0 and 7, so we can put the brackets on the end of our interval. And the two numbers, critical numbers we have in there are 1 and 3. And for r of t, we know those two values make the derivative of altitude 0. And then we can test in between there. Well, if we test 0, because it's a non-critical number, 0 would make 0 minus 3 would be negative. 0 minus 1, negative. Negative times a negative is positive. Between 1 and 3, we could test 2 minus 3 is negative. 2 minus 1 is positive. Negative times a positive, negative. And between 3 and 7, you could test 4 minus 2 is positive. 4 minus 1 is positive. Positive times a positive is positive. So what this shows us, remember, this is the derivative of the altitude. So this shows us that the altitude is increasing, decreasing, and increasing. So we want to know the change in altitude during the time the altitude is decreasing. Well, now we know what that interval is, don't we? We know the altitude is decreasing on this interval from 1 to 3. So that is going to become our lower and upper limit here. From 1 to 3. And we have r of t, which is t squared minus 4t plus 1. And you can see there's no function inside here. And these are just add subtractions, so we can integrate each one separately. So that'll give you t cubed over 3 minus 4t squared over 2 plus 3t. Evaluated from 1 to 3. That would simplify just a little bit. The 2 goes into 4 twice. So that becomes 2t squared. So we first substitute in the 3. Well, 3 cubed is 27 divided by 3 is 9. Minus 3 squared is 9 times 2 is 18. Plus 3 times 3 is 9. And minus, substitute our lower limit of 1. 1 cubed is 1 divided by 2, so that's 1/3. Minus 1 squared, 1 times 2 is 2. Plus 3 times 1 is 2. So you can see that's 18 minus 18, so those reduce out and just become 0. Minus. Here we've got 1/3. 3 minus 2 is 1, so 1/3 plus 1. So you get negative, well that's 1/3 plus 3/3, so that would be negative 4/3. And the units here, notice this was in meters per second. But once you integrate, it gets rid of that per whatever it is. In this case, per second. So this just goes back to meters. And let's think, does a negative answer make sense here? Well, the change in altitude during the time the altitude is decreasing. Well, if the altitude is decreasing, shouldn't the change be negative? Then it is. So it does make sense. If we were trying to find the change in the altitude during the time the altitude was increasing, then we would expect a positive answer. But notice on this one, if it said when the altitude is increasing, we would have had to use two integrals, from 0 to 1 and 3 to 7, and then added those two up. All right, let's take a look at another applied problem here. This one says a pizza heated to a temperature of 400 degrees Fahrenheit is taken out of an oven and placed in a 75-degree room at time 0 minutes. The temperature of this pizza is changing at a rate, so again, that's another word for the derivative, of -3 square root of t, and the units are degrees Fahrenheit per minute. To the nearest degree, what's the temperature of the pizza at time 4? So again, the way you can tell this is an initial plus change problem. We're looking for the temperature of the pizza at 4 minutes. We know the temperature of the pizza at another time, 0 minutes. And we have the equation of the derivative of the temperature of the pizza. That's all we need. So they don't really give us a function to call this. So just make up something, whatever makes sense to you. Since we're talking about a pizza here, I'm just going to call it capital P of 4 is what we're looking for. The temperature of the pizza at time 4. equals the initial, we're given the temperature of the pizza at time 0, plus the change for the integral from 0 to 4, and we're told the derivative of the temperature of the pizza is given by this negative 3 square root of t. Alright, so now P of 0, careful on this one, this is the initial temperature of the pizza. The initial temperature of the pizza, notice it's heated to 400 degrees Fahrenheit. Tempting to put that 75 degrees there because it's right next to the 0, but notice that represents the temperature of the room, not the pizza. So the only reason I'm telling you that is because that's why the temperature of the pizza is going to decrease, because it's taken out at 400 degrees Fahrenheit and put into a room that's cooler than it. It's going to cause it to cool down. So we've got 400 for the initial temperature of the pizza. Then to simplify this, you could pull out the constant of negative 3. And then we have the integral from 0 to 4. And notice all that's left now, if we switch it out of radical form, it will be easier to integrate as t to the 1/2. Again, be careful, don't subtract 400 minus 3. I don't tend to do that, but it'll be violating the order of operations because you have to multiply before subtracting. So let's wait on that. So we've got this negative 3 on the outside. And then when you integrate t to the 1/2, you end up with t to the 3/2, that was it. Dividing by 3/2 is the same as multiplying by 2/3. Drive it from 0 to 4. Then we can keep simplifying that. You can pull out the 2/3 and notice the 3's will reduce out, so you just have a negative 2 on the outside now. And then if we switch it back to radical form, it'll be easier to evaluate. Instead of t to the 3/2, that's the same as the square root of t cubed. And now we have 400 minus 2. And then we can put in, well, square root of 4 is 2, cubed is 8, minus square root of 0, 0, cubed is 0. So just get 8 minus 0. So that gives us 400 minus 16 equals 384. And the units, we'll take a look right here. The units for this 400 were degrees Fahrenheit. The units for this rate of the change of the temperature of the pizza were degrees Fahrenheit per minute. Remember, once you integrate, it gets rid of that per minute and goes back to just degrees Fahrenheit, which it needs to be in order to combine with this, which is degrees Fahrenheit. So your units would just be degrees Fahrenheit. All right, let's take a look at one more. This one says we've got a city located beside a river, has a rectangular boundary as shown in the figure below. The population density of the city at any point along a strip X miles from the river's edge. Okay, so here's our river's edge right here. So it says if we've got some distance X from the river's edge, the population density is X miles from that river's edge is given by h of x, and the units are persons per square mile. Okay, so what it's saying basically is if you go X miles away from the river's edge, everywhere in the city along that strip, the population density is the same. So it's all based on how far away you are from the river. So there might be, maybe there's more people that want to live along the river, or maybe there's more people that want to live away from the river. There could be all kinds of reasons why people want to live closer or further from the river, which is affecting the population density. But then again, it says write but do not evaluate, so we just have to set this up and not work it out. An integral expression that gives the population of the city. So here, to get this, the units are really going to be what helps us to get our correct expression. So we've got h of x, remember, and the units are persons per square mile, or people per square mile. Same thing. And we want the population. Well, the population, that's our goal. That's just persons or people, right? In other words, we need to get from here and get rid of that mile squared. Well, looking back at the diagram of our city, the first thing we can do is notice, well, everywhere along this 8 miles, the population density is exactly the same, isn't it? So, if we just multiply this by 8 miles, look at what happens. Well, that will cancel out one of these that is miles squared, wouldn't it, in units? So then, if we just have 8 times h of x, now the units will be a little closer to what we want. Now it'll just be persons per mile. However, we can't do the same thing across this 3 miles and just multiply by 3 because it's changing as we get further away from the river, right? Based on that. But what we can do to go from persons per mile back to persons is to integrate. So we can integrate this. But to integrate it and get the answer here, we have to know what x is going between. Notice x here is 0 miles from the river, and x here is 3. So it'd be the differential from 0 to 3. And remember, when you integrate, it gets rid of that per whatever it is. So now the units for this would be back to just persons or people, which is what we want, expression for the population of the city. So if we knew what that population function h of x was, this integral would give us what the population of the whole city is. And that concludes the notes for AP Calculus on the topic of the first fundamental theorem of calculus revisited, also known as initial plus change